Okay, I think we are ready to go. Thank you for joining us for today's webinar, Introduction to BMS and Data Analytics. Today's webinar is being presented by Tom Hopton from BuroHappold and Oliver Lockhart from Hoare Lea. But before we introduce our speakers, I would like to cover a few housekeeping topics. So today's webinar is being recorded and the record will be available on CIBSE website soon. The webinar is estimated for 1 hour with a Q&A session at the end. You should all have your mic muted and the camera should be turned off. Please use the chat box for a question at any point of the presentation. If you think of any question for the speakers, just type it in there and we will use them later and answer at the end of this presentation. Also, for those of you who have not heard about YEN before, we are a network of professionals whose mission is to help young engineers to establish themselves in the industry and build their network through technical and social events. If you are interested in knowing more, please follow us on LinkedIn or get in touch with me after the webinar. Contact details will be at the end of this presentation. And now Monica will introduce our speakers.
Welcome everyone. So today's event will be made up of 3 parts. We'll start off with a presentation from Tom. Tom is an associate at BuroHappold with 15 years experience in the built environment industry. He is a fellow of CIBSE, member of Building Control Industry Association, a panel member of the ICT and control groups, and part-time lecturer. Tom is passionate about better buildings and the role that technology can play to unlock building performance in its holistic form. Also, earlier this year, Tom picked up the CIBSE Building Performance Engineer of the Year award. Following Tom's presentation, we will hand over to Oliver, who works as a performance engineer for Hoare Lea, focusing on what can be done to make our buildings perform better. Oliver has led and supported many BMS optimization programs and is particularly interested in how the built environment could and should leverage building data to support real data-driven building design. Ollie is also the committee secretary for CIBSE's Young Energy Performance Group. So that's our speakers. As Ewelina mentioned earlier, we will host our Q&A session at the end, but please feel free to pop your questions into our chat as we go, and we'll just pick them up at the end. And we'll try to get through as many as we can, depending how much time we've got left at the end. And now we'll move on to the presentation. So Tom, whenever you're ready, take it away.
Muted. Thank you, Monica. I'm just going to share my screen. Can I check you can all see that?
Yep.
Yep. Okay, so yeah, thank you, and it's a pleasure to talk to you this evening. As Monica explained, I'm going to be talking about BMS analytics and how it's enabling many of our clients to realize higher performance. But before I go into kind of the nitty-gritty of BMS analytics, I guess I wanted to make a quick note on where we currently are. COVID has put a lens to many trends that have been around for some time. Health and well-being has always been important, but it's top of the agenda right now, and bringing with it new attitudes to healthy buildings, which will likely stay with us for some time past COVID. Monitoring more parameters relating to indoor air quality, enhanced ventilation, UV filtration, and many more kind of features enabled through controls help us build out our resilience to COVID. And that's a positive acceleration of the healthy building trend. Hopefully, COVID will pass at some point, but in its wake, we can expect a recession, and we must look to controls again to create adaptive buildings that can be healthy but do so whilst minimizing cost. And the third wave there potentially the largest wave of them all is climate change. And let me rephrase that. It's not climate change, it's climate crisis. And this is set to redefine our understanding of unprecedented. And so taking control of our buildings, making them adaptable, making them highly efficient is the challenge we must all kind of rally to support in our work. So there are many pieces to that puzzle, and I believe technology and how controls in our building management systems are designed, how they're procured, how they're commissioned and operated are a key piece. Reducing energy demand is key, but creating systems which are more intuitively controlled, environments which make people more comfortable, productive, where space is more effectively used, and systems which support efficient and effective operation is vital. It's vital that we build resilience to really quite unprecedented challenges in our industry and ultimately move towards a zero carbon future. So I guess we don't have all the answers right now, but we do know we need to accommodate change in the future. And that change is to respond to clients that are striving for greater efficiencies in operation, greater business effectiveness, and landmark shifts in national and regional government policies that move us towards that net zero carbon future. Buildings exist for many years, and it's about 80% of buildings existing today that will still exist by 2050. Building refurbishments may be done a few times over the life of the building, and the control hardware, if we're lucky, might change every time we do a refurb. But between these periods, the software hardly ever gets updated, and that needs to change. Designers and operators need to recognize that change is the new norm, and it's a continuum. And we only need to look at how fast technology changes. And as it does change, it becomes more accessible and cheaper. So yes, we need to respond to immediate needs, which may be to reconfigure a space or upgrade a system. But in doing so, and in the gaps in between those periods, we should be making sure our buildings are running on the latest technology, the latest software and programming. And maybe that is machine learning, or maybe it is artificial intelligence in the future. But today we need to be aware of this and ready to respond and capitalize on that potential in the future. So where is the opportunity? Well, it's looking at building performance in a holistic context, and supported by a broad spectrum of technology that monitors and controls. It looks to pull down the bottom line costs of a building and increase a building's yield. So how do we get more from a building, its output, whilst injecting less into the building, its input? Operational efficiency and efficiency of energy use is key, but let's not forget the other inputs, embodied carbon in the physical asset of the physical building and the systems within that building. And let's not forget the carbon and cost and energy associated with the FM activity in a building, both in the material assets of FM, but also in the human resource to support that FM activity. So they're bottom line metrics. Top line metrics are about increasing the building yield, utilizing space more effectively, enriching a building's user experience. So they want to be in that building in the first place, and also to use it more. And a key part of that is user centricity, right? It's addressing their needs and providing an environment that allows them to thrive at the activity that they come into a building to do the work that they must do. I'm sure I've got another slide after this. So those top line benefits are about business performance, and we believe true sustainability is not just about carbon per meter square metrics, which in itself is somewhat arbitrary kind of benchmark. but instead should also consider how productive a building is in its outputs. So when we pay attention to controls and BMS, we can find value and identify really quite high return on investment across the spectrum of building performance. So in terms of the BMS, there is a more holistic value stack that I would like to table here. And in many ways, I feel the industry has lost sight of the full value stack that a BMS can bring. Perhaps that's too much of a blanket statement. And, yes, of course, there are good examples, but I happen to think, and I've seen many more kind of mediocre or even poor examples. So we need to start with good foundations of education, visibility, trust, and collaboration. That needs to be embedded in our industry, and we need to build up from that in our designs, which consult better in this discipline, designs which are extendable, flexible, reliable, and absolutely they need to be efficient in carbon and cost, but they also need to better support FM and do that whilst getting the most out of the top line of our buildings. I mean, I personally think we need to rethink our approach in this discipline a little. Perhaps do better in the way that we consult, do better in the way that we procure designs, and the way that we manage contracts, and also acknowledge that there is a skills gap in consultancies and in the BMS industry too, which is leaving us with outline performance specifications and contractual framework where competitive tenders and program pressures squeeze the value throughout the process, but crucially in that commissioning phase where all the value is often missed. So there is guidance and there are processes we can follow. The BCIA guidance, BCIA is the Building Controls Industry Association. They've got a website which is packed full of guidance. I can recommend kind of taking a peek at that. The images on this slide are the output from a process we follow to justify and protect the energy value in a control design. We built a tool from the good foundations of a British standard, BS 15232, which I think is extremely valuable, but severely underutilized in our industry. It's used to benchmark the energy performance of a controls installation, not just the HVAC, but lighting and blinds too. And the aim of it is to protect the value in a controls design by justifying its kind of energy return on investment, and also trying to protect it from often misplaced VE, and BMS systems are often the target of that kind of VE exercise. So a building management system has certainly come a long way over the last 40 plus years. But what has worked up till now to get us where we are needs to evolve further to take us where we need to be in the future. Integration is becoming cheaper with wider adoption of open protocols, albeit there's a lot of grey area in open protocols. Simply specifying BAPnet is not really enough. So we need to focus on the form and context of data, not just a protocol that carries it. There is still quite a bit of work to do in that respect, but it's happening, and when it does become the new norm, we will catch up in many ways with other industry sectors, and hopefully actually be part of this fourth digital revolution we all hear about. And here's where I shift the focus to the operational phase of a BMS, and one area that's really seeing quite unprecedented market growth is BMS analytics. And there are lots of approaches we take when reviewing the performance of an existing BMS. This slide is the output from an exercise we term as a BMS health check. It's when we go into an existing building and we want a quick picture of a BMS installation. The BMS manufacturers to leverage their tools and software. And these images are taken from a report that Trent produced for us recently. They allow us to take a picture of several different aspects, such as the longevity of an installation. Is the hardware still available? Is it still supported? Is the firmware up to date? As well as highlighting suspicious set points. You know, are the set points too high, too low? And in addition to that, you know, is the installation secure? Does it have sufficient permission and password protection? All valuable intel to kind of help orientate our direction of travel. And sometimes that leads us to the next step, which you know, these images here present our energy assessment tool. And this time we're not using it to appraise new builds. We're using it to identify opportunities for making interventions in existing BMS installation. So, for example, what would the likely return on investment be if we were to intervene and add room demand control on a space heating circuit? Or what would the ROI be if we were to upgrade the controls on ventilation, cooling, lighting, or even blinds? This tool and the one on the previous slide really help orientate our understanding of where to put our efforts, so that our efforts have the biggest impact. So I mentioned on a previous slide the need to focus on the data, and that's really because there's so much value that can be mined from it. You know, I often think that we need to treat data as a valuable asset in the same way that we treat, you know, the physical assets in our buildings. Buildings generate huge amounts of data. Control systems, in the most part, have limited capacity to consider, you know, historical trends within that data and react accordingly. And the new analytical and diagnostic software, which is, you know, in the market at the moment, can crunch these large data sets across multiple systems. They can hunt for patterns which highlight cost savings, carbon savings, health and well-being metrics, or even patterns in equipment behavior which may lead to premature failure. But in our industry, unfortunately, building data is often messy, and if not tagged for its context, these tools struggle to understand its meaning. So new standards such as Haystack and BRIC provide an industry-wide naming convention, unifying data across disparate systems from disparate suppliers and across disparate buildings. And when we deploy these standards, we allow code to be written, useful not just for one building, but it can be dropped onto any number of buildings, sharing the investment and increasing the value. There really is so much value that can be mined from building data, and so much value in sharing this knowledge within our industry. So analytics, you know, if you've ever typed in BMS analytics into Google, you'll be returned with a flood of solutions, and quite honestly, it can be a bit of a minefield to pick out the best fit for your needs. There are some very good products out there and growing evidence of case studies demonstrating the value that they can bring to our industry. I would personally advocate for greater transparency and standardization in this field of engineering. You know, some very good products out there, but there's not too much depth or understanding of what's going on underneath the hood. So is it truly machine learning, or is it simply rules applied to a BMS that wasn't that well commissioned in the first place? I think in general, this industry is doing really good work, but again, you know, I'd like to see a bit more transparency. Nobody likes a kind of black box technology, and this is one area where we may be falling back into the old days of kind of vendor lock-in and kind of closed proprietary protocols. So the image shows how we break down analytics into definable categories. As we progress from left to right, we should expect a reduction in human input. that human input needed to make a qualified decision, and that qualified decision leading to more focused action and a faster return on investment. So here's an example of our own diagnostic approach. It's essentially POE, but on data steroids. It was a measurement and verification appointment in the US. And this dashboard was tailored to, the requirements of the estate director. This particular project had nearly 20,000 control points and time series data in excess of 1.6 billion. And so we needed new techniques. We couldn't pull out our old Excel spreadsheets. So we collected the data. We semantically kind of tagged the data with a haystack and a brick. And we did that so that we could describe each point and understand its context. We then wrote code to go hunt in and amongst the data to find improvement opportunities in comfort, energy, and maintenance. And this particular project performed extremely well. It was in the top 3% of similar buildings. But an almost forensic diagnostic look at the data and the control programming allows us to identify the ceiling of optimization and through cost or carbon savings justify the intervention needed to achieve it. And on those interventions, we tailored this dashboard to the FM team's requirements. We provided prescriptive instruction against each opportunity, which moved from understanding energy consumption to quantifying the opportunity and crucially what we needed to do. With greater understanding of controls, the behavior of systems in operation and understanding of the data that they produce, we can realize the full potential of optimization and really start to close the performance gap. And actually the important lesson here was that we didn't need to change any physical attributes. We were using the technology we already had. We were fine-tuning systems to achieve pretty significant carbon and cost savings. And through this dashboard, we presented our findings around occupant comfort and productivity. We have a number of researchers in BuroHappold that are industry experts on well-being and productivity, and we collected the academic research and we've unified it into a model and exposed this to our BMS data. The step change was, again, prescriptive diagnostics that quantified the impact. We contextualized the BMS data, mapping the average number of occupants per sensor, also mapping the lighting PIR sensors to understand utilization, and quantified the number of hours with potential productivity loss. And on the table on the right-hand side, we expose a clear schedule to FM, allowing them to interact with the data, to drill down and understand whether it's an underheating situation, an overheating, or a ventilation problem, but with prescriptive advice behind that on likely cause. And this was used by FM to prioritize and focus their efforts. The top 5 actions there, when compared to the client's kind of average staff salary, equaled about $42,000 per year, which in context with the energy savings was about half. So there is a justifiable effort to not only reduce energy consumption but try and increase the building yield. And you might ask, well, what do I do if I don't have BMS trend data? And quite often we come across this. Well, we pulled this dashboard together in just a couple of days. It pulled data from IoT sensors with only limited temperature and COT data. We're able to extract insights beyond just the internal room environment, quantifying its impact on occupant productivity, but assessing the air tightness of the building and by measuring decay of kind of CO2 during the night, and therefore assessing the energy, carbon, and cost impact for poor air tightness. And looking at the influence of people on the environment, shifts in CO2 again, temperature, RH, and light levels, we're able to draw conclusions on how well the space is utilised. So there's lots of metrics there, lots of insights we can gather from only limited data. And I think this might be my last slide. So, so where might we be going? Building data has value. There's certainly value to the stakeholders within an organisation, but we live and work in a society where wider society has a stake in what happens in the built environment. And I believe we need to accelerate the building optimization marketplace and make this more competitively driven on open public data. And in doing so, move beyond a single kind of one-way transaction of data service value. Building data holds value to multiple stakeholders outside of the immediate building or client. If we can share data more openly and with more granularity, we can service greater value. And that would and should include how designers can learn from existing buildings, but faster, and how these data sets can support infrastructure initiatives. Buildings are consumers of energy from a grid that is becoming more strained and more sensitive to building loads. Buildings have a part to play to alleviate that pressure. And every is government. Government could make more evidence-based strategic policies around, tax-funded investments. To give one example, I recently measured CO2 levels in an existing school building and found the levels were in excess of 5,000 parts per million for nearly 70% of the occupied time. These levels are proven to severely hinder cognitive performance, and as a consequence, academic attainment of the next generation. So, if the education minister had a clearer picture of this, would it focus their investment priorities? There are just loads of use cases for sharing building data, and I believe the potential for building analytics is pretty huge. So I'll leave you with a couple of quotes that resonate with me, and I don't know, Monica, are we saving questions to the end?
Yes, let's go through Ollie's presentation first and the questions at the end.
Okay. Over to Oliver then, I guess.
Okay, thank you very much for that, Tom. Let me quickly share my screen.
Stop sharing.
Can you all see that?
Yep.
Yes.
Yeah. Okay, perfect. So as Monica mentioned at the start, my name's Ollie. I work for a company called Hoare Lea. And for those of you that don't know, Hoare Lea is an MEP design consultancy. So what that means is my colleagues spend most of their time designing the mechanical, designing the electrical, designing the public health services in buildings. However, Hoare Lea has a number of specialist groups as well to support this work. And I work in one of those called the Performance Group. So the whole purpose of our group is to work in operational buildings, looking into how they're actually performing compared to how they were designed to. And so that's the angle that I'll be talking about building management systems from today, the sort of operational side. Okay, so Tom has obviously gone over in a bit of detail about the sort of where we are with building management systems and what we can hopefully expect over the next few years. And I wanted to go into a bit more detail on a point that Tom has touched on, and that's data. So the information you can get out of the BMS and the way a BMS controls is really only as good as the data and the monitoring that goes in. So it's really important that we're monitoring the right stuff, because at the moment, we probably aren't. And one of the things that I'm always trying to push, and I'm a really keen advocate for, is that we're learning from our previous projects, our previous designs, and a BMS, and really specifically its data, are great tools to show us what worked. and what didn't. But before we get too stuck in to BMS data and analysis, I wanted to introduce you to this, because this is a part of what makes control systems so important, and that is that buildings don't perform how they were designed to. This is a study done by the Better Buildings Partnership, and it compares how efficiently buildings are designed using EPCs to actual measured energy consumption for those buildings. And this is from 2019, so it is reasonably new. And with an EPC, an A indicates an efficiently designed building, and a G indicates a not very efficiently designed building. And so what this chart here demonstrates is that seemingly regardless of how a building is designed, they all seem to perform the same. And this, in essence, is the performance gap, and it is a really big problem for our industry. But there isn't just one thing that we can point to when trying to explain why the performance gap exists, because in reality, it's a complex issue with a lot of contributing factors. One of the key causes, however, of the performance gap that people do often point to is building controls, and that's clearly what we're here to talk about in a little bit of detail today. So whether we're trying to close the performance gap and drive the built environment towards net zero, or if we're only really focused on the sort of day-to-day operation of a single building, the control systems, the building management systems, and really specifically their data play a key role. And that's, in my opinion, for two main reasons. And firstly, that's because the BMS data allows us to check that our buildings are performing as we hope they would, as we expect them to. And secondly, and this is a point that Tom touched on towards the end there, BMS data can provide us with real evidence of how our buildings are performing. And it's something that we can use to learn from for our future projects. So just one final side note, I guess, before we get a bit more stuck in. So I think we all know this. This is the London Plan's energy hierarchy. So that's be lean, increase your energy efficiency, be clean, supply energy efficiently, be green, maximize the use of on-site renewables, and finally be seen. So that's monitor and declare actual energy usage. And for those of you that don't know, the current London Plan draft proposal sets out that be seen requirement for all major developments to monitor and to report on their actual operational energy performance. And whilst this is all about energy data, I think for me, it shows that there is recognition at policy making level of the importance of data for closing that feedback loop. And so I think those are principles we really should be trying to apply to BMS and building management system data. Okay, so clearly data is crucial to ensuring a building is going to control as we would like it to. And there might even be some lessons we can learn if we are able to interrogate that data properly. But what data is it that we need, and what data is it that the control system needs? And to illustrate that, I thought I would just run through a very simple example. So this is a BMS graphic of a air handling unit, a reasonably straightforward air handling unit. So we have the supply fans, the extract fans, the heating and cooling valves, we have the filters here, and some fresh air and recirculation dampers, all very simple stuff. And so what we first want to have a think about is what sensors, what data we're going to need to allow the BMS to control as we would like it to. And so for handling, typically, we might want temperature sensors on the supplier to control the heating valves, to control the cooling valves. We might want CO2 level sensors to determine how much fresh air the air handling unit needs to provide to satisfy the building demands. We may want an outside air temperature sensor to inform any weather compensated controls if we have them. And then, of course, we need the control signals to the fans, to the valves, the dampers, telling them how to control what to do. And once we've had a think about what data it is that we need, we then need to have a think about how frequently we want the BMS to record that data. So the chart here shows the energy consumption of the lighting system on a single floor in an office block. And this data is recorded monthly. And this data doesn't really show us a huge amount of information. However, this is that exact same data, but instead of being recorded monthly, it's now being recorded daily. And already that is starting to offer us far more interesting information. So clearly the data here shows that the lighting system is setting back over the weekend as the office becomes less occupied and is consequently using less energy. However, we can go one step further than that. This is the exact same data, but instead of daily, is now recorded every half hour. And this provides us with a massive amount more information. So we can begin to see the profile of the energy consumption here, where we can begin to compare the energy consumption during the day versus overnight. And we can see that there is a peak in energy consumption there in the middle of the night between about 1 a.m. and 3 a.m. And that, what this data has brought to light, is that is something that probably needs investigating, because that is something that probably isn't right. So thinking about the resolution of that data we're recovering from building management systems that's going to make it useful to you or make it useful to the building manager is really, really important. And just another note on resolution of data. The charts above show the heating demand on a boiler. And so the top chart there shows the boiler's demand recorded every 15 minutes and seems to show the boiler running reasonably consistently. Whereas, on the other hand, the bottom chart shows the data recorded as the boiler turns on and turns off. And so this is referred to as change of state. And as it changes state, perhaps the boiler doesn't look to be operating quite as consistently. And so for some systems, collecting data as it changes state might be more useful than regular recording every 15 minutes, every half hour. So something to think about. And so if we go back to our example AHU, and these are some of the things that are going to be useful for the controls. We have the temperature sensors to control the valves. We have the CO2 sensors to control the dampers, the pressure sensors to control the fans, that sort of thing. And then once we've had a think about what data we need, we then want to think about what data is going to be useful for us to begin diagnosing any issues that may start to pop up. So if we take the image above as an example, so in this image, the air is in this bit of ductwork is moving from left to right. And even though the BMS is asking for the heating valve to open to about 50%, the air temperature has hardly increased. And if all we have is this data, we don't know if the heating valve is stuck and not opening. We don't know if the heating system's turned off. We don't know if the cooling valve is letting by and allowing chilled water through the coil. We don't know if the temperature sensors are faulty. And so we also need to have a think about what information is going to allow us to understand why our building systems aren't performing as you might expect them to. And so back in the case of our air handling unit, you might want feedback from the heating and cooling valves telling you their actual position rather than just the control signal. For the fans, you might want feedback from the inverter itself telling you what speed, perhaps in hertz, the fan is running at. And you may also want a differential pressure switch across the fan to tell you that there's airflow, that sort of thing. And I guess all this data, all this monitoring helps you to understand exactly how the AHU systems are controlling rather than just what the BMS is asking them to, which is really, really important if you want to start running any diagnostics, any of those kind of exercises that Tom touched on. And again, another point that Tom touched on is about integration and using common building protocols, and that's sort of a step further than feedback, really. So integrating with a chiller, as an example, using BACnet might allow the BMS to begin monitoring extra data that the chiller monitors, but the BMS wouldn't naturally. So things like perhaps the actual fault codes, perhaps the number of run hours on the chiller, perhaps even the capacity it's running at. And with this level of integration, with this high level of integration, you may even be able to begin to write information back to the chiller, such as temperature set points and that sort of thing that will allow the chiller to control to. So all this additional information can become really useful when trying to understand the system and I guess more specifically trying to fine tune the system. And so in the case of our AHU, we might want to integrate with the inverter to start getting more detail about how that inverter is controlling the fans, controlling their speed and its health. And then we also want to make sure we've got all the data that we're going to need to verify that our systems are working as we might expect them to. So even if it doesn't really serve any purpose in the control strategy. So this chart here, as an example, demonstrates the electricity generated by a PV array, by a solar panel array, versus what was expected. So the outline there is the predicted energy generation, and the solid bar in the middle represents what was actually generated. So if we look at that period in the middle between October and December, we can see there's a bit of a drop in the amount of electricity generated compared to what was predicted. And was this, in this case, because there was a fault on the system? Was it because of the weather? And without the right monitoring in place, you really just don't know, and you can't know. So it's important to think about what data you might be able to collect that's going to allow you to verify that your building systems are performing how you would expect them to. And so in this case, perhaps that would have been a solar intensity sensor, or perhaps something like that. And so back in the case of our AHU, this might be fairly limited, but you might want to know the energy consumption of the fans. You might want to know how much thermal energy is being delivered to the heating coils, the cooling coils, so that you can begin to compare these systems to how it's expected to perform and how much energy you had expected it to use. And perhaps we need to start thinking beyond what is currently standard, because ultimately we want to be creating spaces for building users to be healthy in, to perform well in, because at the moment maybe we aren't. So should we, for example, be measuring NOx levels? Should we maybe be measuring things like PM 2.5 levels? Should we even maybe be measuring things like heart rates to determine what's the best environment for our users? And if that's the case, where should we be measuring that kind of information, and how? And what are the best systems to collect that data? We also want to think about what other systems, what other building systems we can interface with, so that we can start getting useful information from elsewhere. So one of the really good examples is occupancy data. And so BMSs don't typically pick up occupancy data very well, but a system that does is security control systems. And perhaps you want to start interfacing with those kind of systems to start getting more interesting data to allow us to normalize a building's behavior. And if we're talking about creating spaces that allow users to be productive in, we need to think about what productive means for that space. And so here, for example, that might mean a good sleep, whereas here, on the other hand, probably not so much. And so we need to think about if there is any other data that we can gather through the BMS or through any other systems to allow us to measure whether that environment that we're providing users with is allowing them to be productive, and to think about what that data might be. And then we also need to have a think about what data we should be collecting to understand what worked in those buildings and what didn't, so that we can feed any of those lessons back into the design stage, into our future projects, because that's exactly how the REBA plan of work is laid out. But I think as an industry, this is a step at the moment that we really don't do very well. So with that in mind, I wanted to show you this. So this is a chart that shows the cooling demand profile of a shopping centre in London. So it shows that for about 75% of the year, the cooling load was less than 5 watts per metre squared, and it tapers off here until the peak load of about 30 watts per metre squared. And what's interesting about this data from my perspective is this. So that yellow line there is the installed capacity of the system. And so do we think that a cooling system that is sized for that capacity is necessarily going to operate efficiently at low loads, even though we now know that generally that's where the building spends most of its time? Well, again, that is data we can collect. And for this shopping centre, we have actually collected it. And so this chart shows how, as the cooling demand of the building reduces, so does the efficiency of the cooling system. And the cooling system isn't operating efficiently simply because it wasn't designed to operate efficiently at those low loads, even though that is where the building now spends most of its time. So, of course, it's important to size your systems to deal with the peak loads, but it's really equally important to make sure that systems are going to work efficiently at the loads they are most likely to operate at. And perhaps these are the kind of lessons we need to be learning, and we need to be feeding back into our design teams, that we can think about So we need to have a think about what data is going to allow us to do this. And once we've collected all that data, or at least all the monitoring, there's some pretty smart things we can begin to do with it. as Tom has mentioned and touched on, there has been a boom in BMS data analytics over the last few years, and I expect that's a trend that's probably going to continue. Data analytics, there's a load of data analytics packages out there. They all do similar sorts of things to varying degrees of success, but generally they ingest BMS data and can estimate energy consumptions. They can provide some fault detection and some diagnostics. They can monitor the performance and comfort, and generally this is all provided to you via a dashboard. But building management systems themselves have, in fairness, come a long way and can do a lot of the more basic elements themselves. So just to summarise the sort of analytics you can expect to find, we'll start with this. So this is a dashboard. So dashboards are really the front end of the analytics, or the user interface to the analytics. So they're generally pretty flexible, and they will generally highlight any key actions or findings that the analytics has thrown up. So this dashboard here, as an example, shows that a number of areas for improvement have been identified, though only a few of those have been actioned. So these are sorts of things you can expect a dashboard to sort of provide you with. And then we've got performance and comfort monitoring. And this is where the BMS or the analytics package will monitor and highlight systems not performing as expected or perhaps as designed to. So in the example above, the analytics platform was monitoring space temperatures throughout a floor of an office over the course of a 24-hour period, and highlighting where temperatures have drifted outside of tolerances. And this is that exact same data set, but just presented in a slightly different way. So it shows the number of spaces that are either too hot or too cold against the normal operating times of the building. And so for me, I think the benefit of this kind of analysis is really in the data visualization. It's in the way these packages present huge amounts of information in a really simple, really understandable way, and I guess ultimately a really actionable way. It's really easy to go from here and identify which systems need more attention than others, and that's a really, really useful tool for building managers and facilities managers. Another typical bit of information that an analytics package will present is what equipment is running when it isn't expected to be running. So in the chart above, those red areas are systems that are running outside of normal building opening times. And again, this is a great tool for a building manager, for a consultant to go in and to understand where there might be opportunities for energy savings. And again, this is data that is all available at the BMS, though it's just the way that this data is presented that really makes it useful and usable information. And just going one step slightly further beyond data analytics is the opportunity for a BMS to run its own diagnostics and produce summary reports. So the table above is from a recent handover exercise that used the BMS to check that fan coil units throughout this building were providing sufficient amounts of heating, sufficient amounts of cooling. And so the way this was set up was the BMS opened up all the heating valves of the fan coil units for half an hour. And then after that half hour had lapsed, they tested that the fan coil units were able to provide at least 5 degrees C of heating, and then did the same but for cooling. And whilst these are the sorts of exercises that are great for commissioning and handover, there really is no reason why they shouldn't be continued throughout the life of a building, and because they are great tools to allow building and facilities managers to stay on top of what's working well and what is starting to potentially cause some issues, and where they should start to focus perhaps some of their attention. So just to sum all of that up, I guess building management systems are hugely, hugely powerful tools and do offer a really good potential if we use them in the right ways. So when we're designing and when we're specifying systems, it's really important to remember that we're trying to provide a system that ultimately is useful to whoever the end user is. So always bear that in mind. It's also important to think about what information you, as the designer, might need to learn any lessons about how the systems you have designed are performing. And finally, it's important to think about how we can make the most of the full BMS functionality to allow FMs to stay on top of the building's performance. So thank you for that. And I guess I will pass back to Ewelina. some questions.
Yeah, so basically we have few questions. In the meantime, I saw Tom responded, but we will just bring them here so everyone can actually hear it. Nick, could you please pick up some of the questions?
Yeah. Do we want to start at the first question for this then? I think this was for Oliver. It was asking, in your example, the energy savings in BMS were 27%. Is this a typical figure for modern BMS systems?
So I think that was for Tom. But in our experience, so we've been involved in a number of BMS optimization programs, and if we had saved 27% of them, I think that we would have done very well. I think typically what we've been able to actually achieve are savings in the sort of region of between 15 and 20%. But from Tom's example, that was taking buildings with very limited controls, so those with control bands of D and C, which is sort of on-off sort of control. And if you bump those up to full demand-led control, yeah, you can see those sorts of savings.
And another question for Tom. Are there any specific HVAC systems which usually perform the worst when you're looking at BMS data?
I think that's difficult to answer. I think I put something in the chat. You know, there's lots of variables on any system. Any system that has no demand, no control will be worst. And in the same vein, any NAT vent systems are difficult to maintain control because they rely on humans, and we're not particularly kind of good at maintaining our environments, it would seem. So yeah, okay. Tricky to answer, actually.
In my experience with that, one of the where we've seen there's often quite good opportunities for energy savings is where perhaps controls have been overcomplicated and consequently don't operate the systems as we had hoped or had expected them to. And so quite often there are energy savings associated with just simplifying controls and allowing systems to run more smoothly, more consistently. And so interaction between, sorry, yeah.
I was just going to say there's a few unanswered questions at the end for you. So there was a question on the analytics package and showing comfort temperatures. So would it be difficult to cross-reference that data with external temperatures and mark it against an adaptive comfort standard like ASHRAE 55?
So I think in that, I can flash it back up, but I think what that did is it did compare it to, so if you flip, maybe I'll flip back to it really quickly. See if you can all see my screen.
Do you want to share? Okay.
So if we look here, so these green and blue and red dots, they are individual space temperatures. And so the red line is clearly above 25 degrees C and the blue line marks 21. So all the ones below the blue line are too cold, or the ones above the red line are notionally too hot, as long as there are people in those spaces. And this blue line here in the background, this sort of faded blue line, that's the outside air temperature. So yes, very, very, I mean, analytics packages are reasonably new to the market, and I think they're all, I think they're often willing to be led by what you're looking for and what you're looking to try and show with them. And so if that was something you were interested in doing, then I don't see any reason why an analytics package wouldn't want to take that on board and start monitoring how frequently it is too hot in those spaces compared to outside air temperature.
And I think we touched on this a bit earlier, but there was a question about if there's any typical mistakes that we tend to see in M&E designs, and what would be your advice for designers?
Tom, do you want to start with that one?
Stop using 3-port control valves. Right, that'd be my big. I think just you know, as designers, see a lot of consultancies undertaking designs. You know, you do a heating system or you do a ventilation system, and they put controls in the corner. If you're designing a system, you are best placed to understand how that system works, and really to just, you know, if you're not familiar with controls, just step into that world, because it's important that we deliver integrated designs. We should not farm off the controls package because we consider it to be a black art. It's really not that complicated. It's processes, right? It's steps. How do you see the system working? And it's writing a narrative to support that. So yeah, I see a lot of problems where controls are not considered or not given enough thought. And Freeport Valves.
I think I'd agree with that completely. So we put a lot of effort, a lot of time into designing, say, your heating system, your cooling system, and so there's clearly a lot of thought going in. How that has gone in as to how that might control, but often we're not clear about what we think how that control should look when we pass that over to the BMS company, because all we produce is a performance specification. And so I think if we have an idea of how something should control efficiently, we really need to be passing that on and actually having conversations with the controls contractor so they can see our vision of how that system was intended to operate and intended to control.
Okay, and finally, are there any analytics software tools that either of you would recommend?
So we've got a SkySpark license, which is pretty good. You know, it does a lot of our heavy lifting. Takes a bit of effort to get your head around the programming. It's not that intuitive. The graphics are okay, but they're not that client facing. I quite like the stuff, the demand logic stuff. I quite like. Yeah, that's very client facing. And yeah, I like SkySpark because it's flexible. It's relatively cheap.
One that we've used a couple of times that I've always found very intuitive is Kaizen by Coppertree. I don't know if any of you are familiar with it, but again, I mean, reasonably similar to demand logic. It's just user friendly, and it's easy to navigate around, and it's easy to get to grips with the information it's showing you. And I guess that's kind of key to this is allowing users to be able to understand the analytics as easily as possible.
All right, I think that's all question we had. I think most of them were answered on the chat. So yeah, if you have any additional question, you can either reach out us directly using the contact details I will just share right now.
You've got a question on there about CO2, Monica. School example.
Yeah.
I can post that in the chat if we're out of time.
Yeah, all right, that's fine. Okay, yeah. So unless maybe you can quickly even respond. I think we have that 5 minutes.
Okay. So the question was, with the school example, the reason for extremely high CO2 levels, what was the reason behind this? So it's a good question, and I guess I did a piece of research at Bath College recently where we looked at the effectiveness of kind of occupant controls, and the poor performance in that example I gave in the presentation is a multi-layer problem. One, it was a 1960s building with large windows that were kind of waist height to ceiling height, not good for a winter vent, right? As soon as you crack it open, you get cold drafts right onto the desk. I think there's a big element of behavioral science behind it as well. People don't like opening windows, particularly when you're in a room with others. You know, you're nervous to open a window when you're not sat next to that window because you might affect the comfort of others in that room. I think there's also a social, cultural kind of hang-ups around that as well. And I probably bring my own experiences to that one. My dad taught me not to open windows because I wasn't paying the bills, right? So I think there's an element of that. We may have been poor at the time, right? I don't know. I think training is always useful, but let's be real that training does get forgotten. You know, we might provide some training on practical completion. I can guarantee within 6 months that training is kind of gone. So we need to continue to remind people about that. We did some testing of the CO2 kind of traffic light indicators, and we monitored over about 6 months whether that was actually pushing people to open windows when they should. It had a tokenal kind of improvement. It improved the environmental performance by about 5%, but still, you know, we were still measuring CO2 readings in excess of 2,000 parts per million. So I guess if you want to create that perfect indoor environment, particularly in a classroom, users are the weak link. Sorry.
Okay, yeah, that's education is probably, or training is the most important in like education of the end user, because obviously they don't have to know how to use it because we design for them, but we just need to indicate to them to have it in the most efficient way. Okay, great. Thank you, everyone. We really appreciate you being here. Tom and Oliver, thank you for sharing your insight and expertise. And we'll see you next time. Hopefully you will join our Christmas social wine tasting in December. So please check out our website for more details. You can follow us on LinkedIn as well. And you can get in touch with CIBSE sending email, as you can see now on the last slide. Thank you very much to everyone, and have a nice evening. Thanks.
Thank you.
Bye.
Thanks very much. Bye.
Bye.